Good morning, everyone. Thank you all for attending this virtual session. Thank you also to Kate Bjorkman, Amrit Jalan, and Sanjeev Rao for the kind invitation, for inviting me to present our work in this exciting session. While much of the excitement about AI in chemical engineering is centered around recent advances in machine learning, something which I call as numeric AI, my talk here is going to emphasize the importance of the often ignored complement, which is symbolic AI, the kind of AI that was practiced from 1970s through 2000. And I'm going to talk about the importance of combining these two, particularly for many challenges in reaction engineering and material science in general. Moving on. So as I said, the use of AI ideas in chemical engineering or in catalysis and reaction engineering and material science is not all that new. There's a vast amount of literature on this. There's in fact a 30-year-old literature with several thousand papers published around this topic. Now, before we apply AI to the problems we face in reaction engineering and material science, we need to recognize that our field, our domain, is quite different from that of computer vision, natural language processing, and game playing programs, for example, where it is possible to generate terabytes of data rather easily and rather quickly. Whereas we have the problem where we don't have that much data in many applications. We are a limited data problem. We are really not a big data domain in many applications. I mean, the exceptions may be those where one can generate computer-based simulations and then generate data thereby, such as density field, DFT calculations, that sort of thing. But many problems where we have to do experiments, we certainly don't generate the kind of data that can be generated in vision and game playing programs and so on. And the other important difference is that our domain is governed by fundamental laws of physics, chemistry, and or biology, which are not there in computer vision or in game playing programs. So that's a very important difference. And the third one is that often we would require a mechanistic and deeper understanding of our models, particularly to build credibility and to expand their generality. Now, all these things require combining first principles knowledge with data-driven techniques appropriately. And this is what I mean by saying combining a symbolic AI. This is the kind of AI that was done for about 30 years, or at least 20 years from 1980s to 2000, where symbol representation and symbolic and manipulation of symbol structures was the key breakthrough. With the more modern machine learning developments, which I call as Numeric-AI. And so in this talk, I'm going to identify the challenges and opportunities, particularly using certain examples from inverse design and high throughput modeling. And I classify the problems we face in three categories: the easy, hard, and harder problems. Now, this is just an overview because it's just a 15-minute talk. And if you want to know more about the details, which are discussed in this paper mentioned here. So the problems which I call as relatively easy problems are those where lots of data are available. And then one can use easy to use machine learning tools that is available on the web, random forest, deep neural networks, and a whole bunch of things, Bayesian networks and so on. And such applications are already happening. Estimating physical properties from structures and compositions, for example, determination of structural features from spectral data, yield improvement, a whole bunch of things. Now, this is already happening, so I don't particularly consider them as very difficult problems. In fact, people had shown how to do these problems some 25 years ago, using even the primitive AI tools that were available in the 80s and 90s. So the hard problems are those where we have limited data, and often one of the other three, complex chemistry, system level performance metrics, is what we have to target for, or we need mechanistic insights, or some combinations of these things. Now, these things would require hybrid AI models where we need to combine first principles with data-driven techniques, where we have to build in the underlying physics and chemistry that we already know. Often, we are not totally clueless about many of the problems and systems we work on. We have reasonable amount of understanding. And so the question is, how do you put that in? And how do you combine symbolic AI with numeric AI? Now, let me give you an example of such a problem. This is a problem that was given to us by the scientists and engineers at Lubrizol Corporation in Cleveland some 25 years ago. So they wondered whether we could help them with the design of fuel additive molecules, which kind of look like this. They are long chain molecules with a certain groups for the head group, and then some linker molecules, and then some connector molecules, and then the chain molecules. And typically there are dozens of choices in it, and so the combinatorics is quite high. Now, these are the kind of molecules which are added to the gasoline in order to meet certain system level EPA test, which is called the intake valve deposit test, where the exhaust needs to contain less than 100 milligrams of carbonaceous deposits on the intake valves after running the engine for about 10,000 miles on the road. And now, fuel additives are added to gasoline to minimize that IVD, and the molecules would differ based on the gasoline composition. So it's not one molecule that would work for all compositions. So one has to custom engineer these things given the gasoline that one is trying to sell, and the data in order to do that design is expensive, both in time and in money. Usually it takes about 2 weeks of running the engine to get a single data point. And so it costs about $10,000 per data. And to design these molecules, they needed about 100 data points. That's about $1 million of data points. So this is what I mean by saying this is not a big data problem. This is a limited data challenge. And there are many such examples in chemical engineering and material science. And so one had to leverage the prior first principles knowledge that we know about it. And so that's what we ended up doing. So prior to this work, we had shown how to do inverse design of materials during the time frame using this technique, basically directed evolution in silico. So where we showed that how we can use AI methodologies to go from the structure or formulation of a product to predict macroscopic product performance. This is what I called as the forward problem. This is the prediction problem, but the design problem is the inverse problem. For example, in fuel additives design, we know this property here, less than 100 milligrams, but we don't know what structure of the fuel additive would get us there. So the inverse problem is the design problem. And we showed how to solve these things for polymer design in the late 80s and early 90s. And the details can be found here, using neural networks for the prediction. And then the inverse problem is done by using genetic algorithms, so basically directed evolution in silico. So adapting that technique for the fuel additives, this is the primer. We built hybrid models, which is part first principles and part data driven. The first principles part used whatever physics and chemistry we knew about the problem to identify the key descriptors. We would call them features now in modern parlance, and then correlate those features to the macroscopic properties such as the IVD amount using neural networks or regression techniques, etc. So the underlying physics and chemistry informed us that everything depends on the degradation of this bond and these bonds. So we modeled those things using population balance techniques. So this is the first principles mathematical model using population balance modeling ideas to generate the reactive degradation as the important feature for this particular problem. And then this went into this first principles component, and those are the features, and those were engineered and then correlated with the IVD data, which is where the neural networks comes in. So this is the hybrid AI part, where numerical AI or symbolic AI combined with numeric AI. And then the inverse problem is solved using directed evolution. And so we successfully showed how to design such molecules in silico for fuel additives. And then later on, we did similar things for rubber compounds formulation. And you can find more about those things in these papers. And we forecast at that time. So this work was done roughly 20 years ago, 25 years ago. And we said that in the future, AI-assisted materials design will follow this kind of a path. Now, I realize now that we were about 20 to 25 years too early. So this is the path which people are following now. And then we were just too early to attempt these industrial scale problems using these ideas at the time. Now, coming to harder problems, what would be still even harder? That would be developing Watson-like systems for catalyst design and reaction engineering. For example, we all know about Watson, which is the IBM program that won Jeopardy. So what would Watson look like for catalyst design and reaction engineering? Now, this is not a straightforward apply canned machine learning tools to lots of data kind of a problem. This requires developing chemistry and catalysis specific ontologies, languages, and compilers. And well, that is the kind of challenge we had to face when ExxonMobil came to us with a catalyst design challenge some 20 years ago. And so here it was in the context of zeolite catalysis, and where given the catalyst, it's a heterogeneous catalysis problem. So the final performance metrics such as yield and selectivity depend on the microkinetic reaction network, which in turn depend on the formation and the breakages of various bonds. And that depend ultimately on quantum mechanical structures of the chemistry involved and then the catalyst involved. And so we developed a system called Reaction Modeling Suite, which is an AI-based high-throughput modeling environment for catalyst development, where high-level chemistry rules are hypothesized as for generating the microkinetic reaction networks. And once this is mentioned, the computer automatically developed the detailed microkinetic reaction networks using this domain-specific chemistry compiler that we developed. And then the equation generated converted that into the language of differential and algebraic equations. And the parameter optimizer automatically solved using least squares or other kind of optimization, and then made predictions. And then you saw which, where the model worked and where the model failed. And then you go back and then iterate and fix it. So this was the first time a domain-specific language for reaction chemistry was developed. Remember, this work was done roughly 20 years ago. And a domain-specific compiler was developed, an ontology was developed, and a mechanism which is now we call as active learning was proposed. So for example, the high-level Symbolic-AI component contained rules about what kind of bonds form and what kind of bonds break and so on, based on the understanding of the underlying catalytic chemistry. That input came from my chemistry, catalysis expert, Professor Nick Delgas. This work was done when I was at Purdue. And then, so based on that English language like symbolic rules, we would convert that into this reaction description language, which then converted it to the microkinetic reaction network, and then to the equations, and then to the solutions. So for example, initially, one of the early models we developed, we saw that it was over-predicting C2s and under-predicting C3. And so when my colleague Nick Delgas looked at it, he said, oh, I know what is missing. It needs an alkylation. So now let's add an alkylation step and then make the prediction. And of course, the prediction improved. The point of this is not that we were able to get the accurate model. The point is we were able to get the better model very quickly. See, without the reaction modeling suite, AI environment, to go from hypothesis to model generation and solving the model and then making the predictions would have taken days of work, typically 2 to 3 weeks. Now with this system, we were able to do this in hours. Now, if I were to re-implement the system today in modern computing environments, you could get this result in real time. So the point here is how we can get to the results very quickly. So we proposed this kind of a framework for AI-based materials design, or in this case, catalyst design and model development, which we called it guided experimental design and model development. So basically the human expert using Symbolic-AI seeds the reaction modeling suite with possibilities, and it makes predictions. And then you compare it with data. And if the data, if the model fit is not very good, this bottom loop iteratively improves the model. It also suggests new areas to do experiments and then collect new data. And that's where high throughput experiments would come in. So the top loop improves data collection, and the bottom one improves model refinement. And now this framework has been rediscovered recently as active learning. So we had originally proposed this in 2003. So to summarize, uh, I think the really interesting challenges are in the hard and harder problems. With given lots of data, pretty much anyone can take canned ML tools, machine learning tools, and then show some interesting results. To me, it's not terribly interesting. The harder, intellectually harder and challenging problems are in these kind of categories. How do we build hybrid AI models? How do we build these discovery engines or Watson-like engines, which require building domain-specific ontologies, languages, compilers, etc. And the question is, even though we have demonstrated how to do such things, we need to be able to do these things very quickly. We need to be able to scale such systems quickly, easily, and reliably. And I suspect that it's going to take another 10 to 15 years. We may be still a little too early to attack these kind of problems. Thank you very much for the kind invitation once again. And I would like to acknowledge my collaborators and various funding agencies. And thank you for your kind attention.